Okay, good morning everyone. Let's see. So we're going to carry on with our inquiry into integration, and today we're going to learn a particular technique for doing integration of certain types of functions. So today's lesson is going to be split into 2 days actually. So today we're going to talk about doing indefinite integrals using this method. Next time, on Monday, we'll talk about doing definite integrals with this method, which really just amounts to using this method with the fundamental theorem of calculus. So on Blackboard, you'll see there's actually like 2 exit slips. I put one up that says like part 1, that's today. Part 2 is on Monday. Hopefully that's not confusing. So let's go ahead and start on these warm-up problems. All we're supposed to do for these warm-up problems is just find the inside and the outside function such that if we plug the inside function into the outside function, we'll get the function we have here. So just identifying, no chain rule yet, just identifying the inside and outside function. That one's still working? Okay, seems like we're good. Who can help me with the first one? I want to express h of x as f of g of x. What should f of x be? Well, why don't we use the old notation? We'll call it f of z, and then we'll call it g of x. So, g of x, the inside function. Alice?
X cubed.
Yeah, x cubed. And what do we think for the outside function? Kevin?
3e.
Yeah, 3e. We'll use z because of this notation. If you use x, that's fine too. The only reason I like to use z for the other one is just so that we recognize that these are sort of completely different functions. Okay. Second one, h of x equals 2 ln of 5x plus 7. I did it again. What's g of x? Yeah?
5x plus 7.
5x plus 7, very good. You want to go for gold and tell me what the outside function is?
2 ln of x.
Very good. I'll put z. That's fine. Okay, last one. I'll express this as f of z and g of x. Inside function, what do we think? Kevin?
2x squared plus 1.
Yeah, very good. What does that make the outside function?
Just x to the 1/2.
Yeah, or we could write it as a square root. Okay, so that's just to remind you about finding these inside and outside functions. That's going to be, that's always been an important skill, and it's related to the material of today's lecture, which is called U-substitution. It is, in essence, a way of finding the antiderivative of something which looks like the result of a chain rule differentiation. So, before, we said that the derivative of f of g of x was equal to the derivative of the outside function, where we leave the inside function alone, and then we multiply by the derivative of the inside function. And what we're about to explain is how we're going to go in the reverse direction. So, how do we go from something which looks like a chain rule to the antiderivative? Okay? So in this case, the antiderivative of f prime of g of x times g prime of x is just f of g of x. Okay, so here's how we're going to do that. Okay, so U-substitution. Maybe I should say something about why we use the letter U. Okay, so I'll describe when we should use this. Use U-substitution, which we usually write just U-sub. Whenever we see an integrand that looks like the result of differentiation by chain rule. Okay, I guess I better tell you what an integrand is. I'm not sure I've ever used that word. An integrand refers to this part of the integral expression, the function which we are integrating. We call that the integrand. Okay, so if we see an integral problem and the function that we're integrating looks like it's the result of a chain rule, that's when we should use U-substitution. And here's what we do. Here's the process. We say, let U be the inside function. And let du be du dx dx. Then express the integral in terms of U. Okay, so the crucial step here is deciding what U should be. This is the most crucial step. Once we pick U properly, the rest of the problem will sort of fall into place. Okay? Will sort of fall into place. Okay, I think this is going to become a lot more clear once we do a couple examples, but are there any questions so far? Okay. Let me come up with a better example than... Let me find a really good one for our first one. How about that? Well, I don't like any of these, so I'm going to make my own. I just want to have one that's really, really clear for the first one, because you'll see that later on the process becomes a little bit tricky to rearrange these equations in a certain way to make them look like what we want. So, for example, if we want to take the integral of (3x squared plus 1 cubed times 6x dx. I think this is a super clear-cut case of U-substitution being necessary. Here's why. The first thing we should do is decide what is the inside function. So if this expression is the result of a chain rule, then the inside function is this function right here, right? What it looks like is previously we had this expression like to the 4th power or something like that, and then we multiplied by the derivative of the inside. Okay, that's what it looks like. So here's how we do this process. We look for two expressions in the integrand for which one of them looks like the derivative of the other. In our case, 6x is looking like the derivative of 3x squared plus 1. So here's what I'm going to do. I'm going to choose u to be the inside function, 3x squared plus 1. Now, it remains to choose what should du be. Okay, in our note box, we said that du should be du dx dx. Okay, but that's a little bit confusing. Here's what how I want to tell you to do it in practice. First, just figure out what u is. The next step is to find out what is du dx. Okay, Leibniz notation here. We just want to take the derivative of that expression with respect to x. If we do that, we use the power rule and the multiplication by constant rule, and the derivative of a constant is 0 rule, and we'll just get 6x. So if you want to know what du should be, we kind of just treat this equation as if the left-hand side was a fraction. Now, mathematically, that's not exactly what's going on, but this is how you can think about it. If you guys were math majors, maybe I wouldn't say that like that, but this is how it works in practice. So if we want to figure out what du should be, we just take du dx, we take that expression on the right-hand side, and we just add a dx there. Okay, so I can reformulate this expression here. In this case, if I switch to u and du, this term here looks like u cubed. And this whole thing right here, 6x dx, that's du. So I can reformulate this integral as, if u and du are defined in this way, this integral is the same as doing the integral of u cubed du. Why don't I go back to the colors? We use u cubed du. And that's an integral which I think we know how to do. How should I find the integral of u cubed? Is there a rule I can use? Right now I'm just considering this integral here. Don't worry about what u and du actually mean. I'm just saying that if I gave you this problem on an exam and I said, find the antiderivative of u cubed. Not quite, that's the derivative. But we should use that rule in reverse.
U to the fourth power over 4.
Yeah, very good. This, we're going to get u to the fourth power over 4 plus c. Okay, so now we did that. What we're going to do now is switch back. We know we already decided what u is. Now let's switch u back to what it was before in terms of x. So wherever I see a u, I'm going to write 3x squared plus 1. I don't see any du's, so I'm not going to worry about that. So the answer to this problem is 3x squared plus 1 to the fourth power divided by 4 plus c. where c is some constant. So in particular, the expression I have here, which I'll highlight inside the red box, since we did an indefinite integral, we got a family of functions. It's the family of functions where we take 3x squared plus 1, take that to the 4th power, divide by 4, and add some number. Any number we want. Okay. So that is maybe the most basic chain rule problem that there is. So the game here is to look for, try and see if you see some function, in our case it was 3x squared plus 1, and its derivative, in our case 6x, present in the integrand. That is our clue that maybe we should try using U-substitution. The other clue that we should have to try U-substitution is if we see the integral of something that we just have no idea how to integrate it. Like if I gave you this problem here, I'm not sure that you guys would know how to find the integral of this without using U-substitution. So if you see something that looks really complicated, the first thing that should go off in your head is U-substitution. I should try to express this integrand in terms of some function and then being multiplied by the derivative of that function. Okay? That's what we should be doing. Okay, so let's try problem 1 on our own for about 4 minutes. How about 4 minutes? And the goal here is to do this first step that I did here. I want you to try to identify what should u and du be. Or really, yeah, really just u, I guess. I mean, it's kind of implicit that if we know what u is, we know what du is. So yeah, I guess find u and du. And why don't we say, I'm going to modify the problem a little bit. I'm going to put an integral sign and a dx. I'm going to put an integral sign and a dx. And I'm going to put an integral sign and a dx. And what I want you to do is find u and du, but don't solve the integral. Just find u and du using this process that we used for the first problem. Actually, just do A. All right, for this a here, square root of ln x over x. Has anybody figured out what do we think u and du should be? Or just have a good guess. Totally fine if you don't get it right on the first try. Kevin, what you thinking?
Is u ln of x?
I think you're exactly right. We should set u equal to ln of x. Now we don't need to do much work to figure out what is du, okay? Don't bother using this process of where they say let du be du dx dx, whatever, fine. Just find du dx. Do the derivative of whatever thing you chose to be u. We're going to get 1 over x. And we're going to treat this just like it's a fraction on the left-hand side. It's not really a fraction, but we're going to treat it like it's a fraction. And we're going to write du equals 1 over x dx. Okay? So if I were to write this integral after performing my u-substitution, I would write that this is the integral of the square root of u du. Did other people choose ln x for u? Okay, good. All right. So there's one reason that I said don't do B and C yet, and that's because I should tell you about one more thing before we do B and C, and that is we can perform u-substitution as long as any constant multiple of du is present. For example, the same integral that we did before. It was 3x squared plus 1 cubed plus 1 cubed. But we're going to switch this up now. Instead of writing 6x dx, I'm going to write x dx. Okay, and what I'm trying to claim here is that we can still do u-substitution because a constant multiple of du is present. Okay, so let me do the example and then I'll explain kind of what was going on here. So we're going to do the same thing as before. U is going to be our inside function, 3x squared plus 1. Then du dx is equal to 6x. Therefore, du is equal to 6x dx. Okay, so the issue here is that our integral is not in the form of u cubed du anymore. We don't exactly have 6x dx here. We have x dx here. But I'm going to tell you that it's not a problem because of the rule that we had way back when we said that the integral of c, some function, f of x dx, multiplied by a constant, is equal to just c times the integral of that function. So this is the rule we should keep in the back of our mind as we do this. Here's what I'm going to do. I have x dx here, and I want to express this in terms of du. So what I'm going to do is I'm going to take this equation here, and I'm going to solve it so that I get x dx on one side. Okay? So watch this. 1/6 du equals x dx. So now what do I have? I have this first piece looks like 3x squared plus 1 cubed. That's u cubed. And the second piece doesn't look quite like du, but it looks just like 1/6 du. Okay? So as long as we have any constant multiple of the derivative of our inside function, then we can just do the following. I'll write this as the integral of u cubed times 1/6 du. And I'll write that, I'll just pull the 1/6 right out front. I'll get 1/6 times the integral of u cubed du. So if I wanted to actually find the answer to this problem, I would do the same thing that I did before. I'd find last time I did the integral of u cubed du. This time I'm going to take that number and just multiply it by 1/6. So I'll get 1/6 times 3x squared plus 1 to the power 4 all over 4 plus c. And I don't need to write c over 6, because if I take some constant, which is just some random constant, we don't know what it is, and I divide it by 6, it's still just some random constant. It'll be a different constant, but it doesn't really matter because c is just taking the place of some number. If we take some number, divide it by 6, it's still just some number. Okay, so that's how I would do that problem. So the process for when we don't quite have du, but we have a constant multiple of du, is to sort of take the pieces that we have okay, here's how I want to say it. What we're going to do is take a look at this integral here. We're going to look at what we've already sort of used up in our u substitution. We already decided that u was going to be 3x squared plus 1, and then we're going to cube that, so that's going to be u cubed. What we should do now is take what I like to call the leftovers, x dx. We find du, and then we rearrange this equation until we have the leftovers on one side. And then we will replace the leftovers by whatever's on the other side of that equal sign. That's kind of what we're going to do here. So what I did was I wanted the right-hand side of this equation, du equals 6x dx. I said I want the right-hand side of that equation to look like my leftovers. And so I solved for x dx on the right-hand side, and I just replaced my leftovers by something that's equal to them, namely 1/6 du. Okay, that's kind of the process for when we have a constant multiple issue. Okay. So let's go back up, unless there are any questions about this. Maybe I'll pause for a sec. You guys find the constant multiplier confusing? It's a little bit more complicated. But like with all things in math, practice makes perfect. So let's try B and C now. I'll give you guys a minute or two. Let's try to find out what u and du should be. So the reason that I talked through this thing before I got here is you're going to notice that 2x squared is not exactly the derivative of 8 plus 3x squared or whatever. Wait a second. This is not even... Oh. Okay, look, we're gonna go through this together. Sorry, this problem is really giving me... this is so annoying. Okay. Well, I can't read. The question said, determine if you can find the antiderivative of the following with our U-substitution techniques. If so, find the correct U, and if not, say why not. We'll go through these together, because I really should have... I should have just gotten rid of this problem, but we're doing it. Okay. So, we've got 2x squared times 8 plus 3x squared to the power 5. Okay? And here's a big problem. I can use U-substitution whenever we see an integrand that looks like the result of differentiation by chain rule. And there's a reason why this does not fit that description. Can anyone tell me why this does not look like the result of chain rule differentiation? Kevin?
I think it's 2x squared is the derivative of the inside function.
Yeah. More specifically, we're not going to worry too much about the constant. But x squared will not be the derivative of this function multiplied by a constant. Okay? If we take 8 plus 3x squared and we take its derivative, we get 6x. So, the issue here is that the number which we have being multiplied, or the function which we have being multiplied out front, is not just differing by a constant. It's differing by a power of x. And that will spoil everything for us. Okay? So, what we said on the most recent thing we talked about down at the bottom was that as long as any constant multiple of du is present, we're good to go. However, 2x squared is not a constant multiple of 6x. So that's the issue here, and we would not be able to use U-substitution on this problem. So here's how that might go if I was a first-year calculus student. I would look at this and I would see, okay, this looks hella complicated. I'm going to try to use U-substitution. I think U should be whatever's on the inside. So I'm going to set U equal to 8 plus 3x squared. And then I'm just going to try to find du by doing the derivative of it. That'll be 6x, and then I'll take du equal to 6x dx. And then what I'm going to do is I'm going to look at my original problem. I already know that I replaced 8 plus 3x squared. That's u. And then I'm just going to take that to the 5th power. So what do I want to do now? I want to take my leftovers. My leftovers are 2x squared dx. And what I want to do is make this right-hand side look like 2x squared dx. Right? But I can't do that by just rearranging this equation. I could make it look like, I could divide both sides by 3, then I'd have 1/3 du equals 2x dx. That's close, but it's missing the crucial square here on x, okay? So that's how I might do this if I was a first-year calculus student and I didn't know any better. I might try to find out what u is, but you will run into this issue when you start trying to solve the right-hand side for your leftovers. You're not going to be able to do it. Okay. So that's that. Let's look at the next one. Okay. Let's take the naive approach. Look, it's not naive. It's perfectly acceptable. If I look at this and I'm a first-year calculus student, I see, okay, this looks crazy complicated. Let's try to use U-substitution. If I want to use U-substitution, I should pick what U is first. U should be whatever the inside function is. If this were to be the result of chain rule differentiation, the inside function on any chain rule problem involving e to some power is always the power. So I'm going to set u equal to 2x squared plus x. And from there, I'm just going to figure out what du is and see if I can solve that equation for my leftovers. Okay, so du dx equals 4x plus 1. So du equals 4x plus 1 dx. Okay, so the question now becomes, I've already used up, I'm going to write e to this stuff, that's going to become e to the u. And now I have to worry about my leftovers. 6x dx. So the question is, can I solve du equals 4x plus 1 for some expression where the right-hand side looks like 6x dx? And the answer is no, I can't really do that. And here's why. This pesky plus 1 is going to really create an issue for us. Okay? There's no way for me to transform this right-hand side. I want it to look like 6 dx, and then the left-hand side should look like some number times du. And these two equations are incompatible. We're not going to be able to do that. Okay. The reason being, I can't take 4x plus 1 and multiply it by a number and get 6. X. That's what I want it to be. Okay? The reason is because of the 1. All right, so these two were incompatible with U-substitution. This one was good. Any questions about problem 1? Okay, if you have questions, or if you're totally lost, don't panic. U-substitution is probably the hardest thing we'll do in this class. So we're going to spend a whole nother day on it. We're going to do lots more examples. I have office hours today if you guys want to show up for that. And yeah. So I think I'll use the last few minutes to just, I think it would be instructive for you guys to see more examples of how this is done. And please just interrupt me at any time if you have questions about what I'm doing, because it will really help you if you get those questions answered now. Okay. So I want to do the integral of 2x e to the x squared dx. It looks way too complicated for us to handle using usual antiderivative techniques. So I'm going to try to consider this as being the derivative of a composition of functions. Okay, so the first thing to do is to figure out what was the inside function in the original composition of functions. And this e to the x squared times 2x kind of looks like the derivative of e to the x squared, don't you think? That's what it kind of looks like. So that's my intuition going into this. A lot of the time, they'll flip-flop which side the derivative is on, right? In this case, they put 2x e to the x squared instead of e to the x squared times 2x. It's just to make it more confusing, okay? But don't worry, because we know that multiplication we can do in any order. Okay, so that was my intuition for this problem. Let's see if it's right. I'm going to try to say that u is going to be equal to the power on e to the x squared. Then du would be 2x, du dx, which means that du is going to be equal to 2x dx. And would you look at that? 2x dx exactly corresponds to my leftovers, and here x squared, here x squared exactly corresponds to my u. So I'm going to rewrite this entire integral as the integral of e to the u du. So, hard work is done. Now what we need to do is just a problem like we've been doing for a while now. We need to find the antiderivative of e to the u. So I'll do that antiderivative. I'll get e to the u plus c. And the last step is to switch back to x. So that'll be e to the x squared plus c. Okay? So that's about as simple as chain rule, or as U-substitution gets. Questions about that problem? And when I say simple as U-substitution gets, I'm not saying that it's simple. It's still pretty complicated. But that's a pretty standard example. All right, let's try this one. I see something that looks way too complicated for me to solve using standard integration techniques, so I'm going to try to use U-substitution here. Okay, I'm going to try to use U-substitution. Okay, so I want to think about whether this looks like the derivative of a composition of functions. And it's looking a little bit bleak. But I'm going to rewrite it in a way to make it look a little bit less bleak. I'm going to write it as 1 over 2 e to the x plus 1 times e to the x dx. I think if I write it like this, it'll be a little bit more clear how to break up what should u and du be. Well, I know that e to the x is the derivative of e to the x. So the question now becomes, is e to the x a constant multiple of the derivative of 2e to the x plus 1? And the answer is yes, it is. So let's try u equals 2e to the x plus 1. Okay, this is a common technique if we have a really complicated denominator. We're going to look for a u substitution that's going to give us something like 1 over u du. Okay, and then we'll take the antiderivative of that and get ln u. Okay, so what's du dx? That's 2e to the x. So du is 2e to the x dx. Now that's not exactly what I've got up here. What I have here is e to the x dx. So I'm going to solve this equation for e to the x dx. So e to the x dx on the right-hand side, the way I get it is by dividing both sides by 2, and I get 1/2 du. So I can now write this integral using all of this stuff here. I can write it as the integral of 1 over u times, not du, but 1/2 du, which is just 1/2 times the integral of 1 over u du. Oh geez, I'm over time. Okay, well I'll finish this really fast. This is going to be 1/2 times antiderivative of 1 over u is ln absolute value of u plus c. And then I'll switch back. We'll get 1/2 ln absolute value of 2e to the x plus 1 plus c. Okay, sorry for going over time. Today's class is over. If you have questions or you want to see another example, stay after class. I also have office hours today from 11 to 1. You can connect via Blackboard. The link is on the page. Have a good weekend.